Good day, I'm Norman Wildberger. This is video number 100 in this series on the foundations of mathematics. And maybe it's a good time to pause briefly and celebrate this achievement of having gotten to number 100. I hope to add many more videos to this series because there's still many things that we want to address. We still have to deal with the weaknesses in real numbers in the continuum. We want to then discuss set theory and a lot of dubious aspects about that. And then we want to end up building up a new and alternative point of view towards calculus and analysis. And also perhaps topology and other things too. So still a lot to be done. I think this is probably a good opportunity to dedicate this series. And I would like to dedicate this series to the Australian taxpayers. All right, I'm an employee of the University of New South Wales, but ultimately I am funded by the Australian taxpayer who pays to let me have time to do my thinking and to do research. And without that time and support, it would be impossible for me to have understood the things that I've understood and that I'm able to share with you. So many thanks to the Australian taxpayers for generously supporting my and of course other academics' researches. In today's lecture, we're going to take the first steps towards establishing a theory of so-called infinite sequences, which we would rather call by a different, more modest name. We'll call them ON sequences, short for ongoing sequences. Now, I've stressed a lot the very big difference between finite sequences, which we can pin down completely concretely and which our computers can handle perfectly, and these so-called infinite sequences that have perhaps an infinite amount of data involved in them. These are much more problematic, and we must be more careful and deliberate in our attempts at establishing such a theory. Well, of course, a finite sequence is specified by listing all its elements. Here, for example, is a modest little finite sequence. 1, 3, 5, 7. It's listed there, and we don't have to rely on any other alternative description. The listing of the elements is sufficient. However, how do we define and specify a so-called infinite sequence? For example, how do we hope to deal with the many examples in Sloan's online encyclopedia of integer sequences? Well, the approach that we're going to take is we're going to start slowly. We're going to build up this theory of ON sequences one step at a time. So I have this open-ended view towards mathematical theories. I think that many subjects, including the subject of sequences, is best approached by thinking of it in terms of compartments, small steps that we take and going further and further and further along in essentially an unbounded situation. So we do not hope to capture all at once the notion of an infinite sequence or an ON sequence. We must be more modest in our endeavors and just attempt to cut out small pieces at a time. So that's what we're going to do today. We're going to start with, first of all, constant ON sequences. So, the definition. A constant ON sequence is an expression of the form C equals bracket K bracket for some K a natural number. And notice that the brackets I'm using are a square bracket on the left-hand side and a pointy bracket on the right-hand side, which is supposed to remind us that this is representing ultimately a sequence in our mind, something that has a beginning and sort of keeps on going in that direction. It's just a notational convention that allows us to remember that this is supposed to be a sequence, at least in our minds. So for example, here is an example of a constant ON sequence. It's the ON sequence 1. Here's another one. It's called B. This one is the constant ON sequence 5. Now, associated with such an ON sequence, we have a sort of a secondary and important thing that we can do. So for any natural number m, The mth element of the constant on sequence C equals the on sequence K is by definition this. It's equal to K. So we're defining a new expression, or a new aspect of this expression, that we're allowed to put an index to the right and below, and that index can have any value which is a natural number. And the interpretation of that is that the output is going to be K, the same number that's appearing inside the brackets. So we say that the mth element of the on sequence K is K. So, for example, if A is the constant on sequence 1, so then the first element of A sub 1, is 1. The second element of A is 1. The third element of A is 1. The 174th element of A is 1. All of the elements of this constant sequence are the same. They're all equal to 1. So, for example, also if B happens to be the on sequence 5, then the first element is 5, the second element is 5, the third element is 5, the 1001th element is 5, all the elements are 5. And so, somewhat informally, we can write the following, which connects with our intuitive understanding of what an on sequence is. So we just write down the elements, first one, second one, third one, fourth one, up to a certain amount, and then we write 3 dots. So the on sequence 1 is 1, 1, 1, 1, and so on. The on sequence 5 is 5, 5, 5, 5, and so on. We should recognize, however, that there's something ambiguous about the 3 dots. The 3 dots by themselves do not tell us how the sequence carries on, but this expression here does tell us. It pins down exactly what we're talking about. And in general, our notation for sequences, if the sequence name is A, we'll say that the first element will write A sub 1, and then the next one A sub 2, A sub 3, and so on in the usual fashion. All right, so this is a way for us to generate a sequence in essentially a completely finite way. Right? We only have 3 elements really, the left bracket, the number, and the right bracket. And that little combination is capturing for us what intuitively we might want to think is an infinite sequence. But there's no need to become philosophical about the nature of this sequence, and how does it go on forever, and various, is the universe unbounded, does time go on forever, etc. We just can work with this completely finite expression, with the added idea that at any point we can access the mth element of this sequence, in this case in a very simple way. And now let's also introduce a useful way of visualizing on sequences. So to visualize a constant on sequence, say the on sequence 5, what we're going to think about is perhaps a number line, and there's the point 5. And we're going to think about having a regularly flashing light at 5. Blipping. Blip, 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 maybe every second or every unit of time. For t equals 1, it blips at 5. T equals 2, it blips at 5. T equals 3, it blips at 5. And it keeps on blipping at 5 and doesn't do anything different. So it's a very simple kind of movie, maybe not too interesting to look at. But nevertheless, we can think of this as being somewhat different from the constant number 5, which we can also visualize as simply a constantly lit up point 5. So here we have something different. We have a series of blips always at the same point. It's a way of visualizing or thinking about what the on sequence is, using time as an aid. All right, now we can do arithmetic with constant on sequences. It's kind of obvious because on sequences are really the same as natural numbers for us, and so we can add 2 on sequences in the obvious way. So the on sequence 1 plus the on sequence 5 is the on sequence 6. And if we want to, we can write it in terms of these sequences with dot dot dots if we want to. We can multiply two of them in the obvious way. 2 times 3 is 6. So in general, the on sequence k plus the on sequence L is the on sequence k plus L. And the on sequence k times the on sequence L is the on sequence k times L. And then you can give a little bit of thought to this exercise that the usual laws of arithmetic with natural numbers hold. So we have a complete reflection of the laws of arithmetic with natural numbers here in the universe of these constant on sequences, which are almost the same as natural numbers, but they have a different interpretation. We're thinking of them as a sequence which just happens to not be changing. So now that we have constant on sequences under our belt, let's move up a rung in the ladder and talk about polynumber on sequences. And let's start with a very specific but important new on sequence. It's the expression that's going to look like this. Square bracket, n, pointed bracket. But the n here does not represent a natural number. The n is actually the letter n. The letter n. And we're going to use the letter n and no other letter here. Okay? So this uses the letter n and only this letter. So we've written this thing down. What is it? Or how do we interpret it? Well, we're going to make the following definition. That for any natural number m, we're going to say that the mth element of this on sequence, n, is, here's the definition, the mth element of the on sequence n is m. So the first element of the on sequence n is 1. The second element of the on sequence n is 2. The third element of the on sequence n is 3. Therefore, we might be able to write this, that the on sequence n equals, well, here's the first element, the second element, the third element, the fourth element, dot, 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 to represent, and it goes on like this. This is an informal expression which is ultimately meaningless by itself. This is actually the real expression. So this is some kind of informal picture that we associate to the actual object, which is right here. How do we visualize this new on sequence? Well, we also think of it as a series of blips on the number line. But it's a more interesting series of blips now. It starts here. So at time t equals 1, there's a blip right here. And then the next second, or the next minute, or whatever unit of time you're using, there's a blip now at 2. At the next interval, a blip at 3. And so on. So you watch these things, you see the sequence of blips successively moving to the right. It's like a movie. You're going to have to pan to the right to keep watching it. The series of blips is going to keep on going. Blip, 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 blip. And you can watch it for as much time as you have patience watching it. It never ends. It keeps on going. Blip, blip, blip. Until perhaps, well, there's no more room or who knows what. So it is a succession of blips starting at 1, moving to right. This is a visualization of this new on sequence n. We'll just call it n. And it's really an identity sequence in some natural way. It's a very important new object, and we'll see that it's quite a useful and interesting object. So let me remind you about what a polynumber is. A polynumber is our form of a polynomial. It's a rather more concrete and down-to-earth and specific definition of a polynomial. So for us, a polynumber or a polynomial is just a list of, well, natural numbers or integers, whatever it is that we're working with. So here, for example, is the list 2, 0, 1, 4, which is a polynumber. And we have an alternate form for this polynumber in terms of alpha. Alpha is the polynumber 0, 1. Okay, so this polynumber can be written maybe a little bit more familiarly as 2 plus alpha squared plus 4 alpha cubed. Okay, and we've talked a lot about polynumbers and their arithmetic, and it stressed the importance of them. Now what we're going to do is we're going to use these polynumbers to generate a new kind of on sequence. of which the n that we just defined is the simplest example. So here's our definition. If p is a polynumber, and let's say that we're working with an integral polynumber for now, then the expression Pn in brackets with a square bracket on the left and a pointy bracket on the right, this is a polynumber on sequence. And furthermore, we define for any natural number m that the mth element of this polynumber on sequence is by definition P of m. So note that the polynumber itself always has an n involved. No other letters are allowed, only n's. But if we want to evaluate the mth element of such a polynumber, we substitute the letter n for the number m. There's a bit of confusion possible here. So this n is the letter n. This m is representing some arbitrary natural number. The mth element in this on sequence is by definition P of m. For example, if P happens to be the polynumber 2 plus alpha squared plus 4 alpha cubed, then here is the associated polynumber on sequence. It's 2 plus n squared plus 4n cubed. And we recognize this is a polynumber on sequence in two ways. First of all, there's this square bracket on the left and pointy bracket on the right, which is alerting us to the fact that this is an on sequence and not something else. And secondly, there's n's inside here. N for us, from now on, will often denote an on sequence. Okay, so this is an on sequence, and the first element in this on sequence is what you get when you replace the n with the number 1. In which case you get 2 plus 1 plus 4, which is 7. The second element in this on sequence, it's what you get when you replace the letter n with 2, which would be 2 plus 4 plus 32, which is 38, and so on. So we can generate the elements of this on sequence by replacing the letter n with numbers 1, 2, 3, 4, and so on. This is a polynumber on sequence, or if you like, a polynomial on sequence. The words polynumber and polynomial being almost interchangeable here. These polynumber on sequences that we've defined naturally incorporate the constant on sequences that we defined earlier. Because after all, a constant, like 5, can be thought of, if we want to, as also a polynumber, just a constant polynumber. And the arithmetic of polynumbers naturally extends to an arithmetic of polynumber on sequences. So for example, here are 3 particular polynumber on sequences. The on sequence n, the on sequence 2 plus 3n, the on sequence n squared plus n cubed. And if we want to write them out in a more familiar kind of sequence fashion, we just write out the first few terms and then put 3 dots. So this one here, that's our basic polynumber on sequence n, 1, 2, 3, 4. This one here is the on sequence that starts with 5, and 8, 11, and 14, because I happen to start with n equals 1. And this one here, n squared plus n cubed, its elements are 2, 12, 36, and 80, and so on. So we can do arithmetic with these kinds of things. For example, we could add these two sequences, a plus b. Well, we could either add them at this level here. 1 plus 5 is 6, 2 plus 8 is 10, 3 plus 11 is 14, 4 plus 14 is 18, and so on. Although that's ambiguous because the 3 dots, what does it mean? But more precisely, we just add this one to this one. 2 plus 3n plus n gives us 2 plus 4n. So that's the new on sequence. It's the sum of these two. Similarly, this one times this one, well, we just multiply the n by the 2 plus 3n to get 2n plus 3n squared, and we can write down the elements if we want to, and they are of course just the products of the corresponding elements of A and B. And if we want to, we can do something a little bit more fancy. We can create combinations of things. For example, we could take 2 times this sequence plus 3 times this one squared, which is better to think of at this level here. So 2 times this plus 3 times this plus this thing squared. Well, that's a computation that we basically make in the world of polynumbers, and then we get some new polynumber, and then we just make an on sequence out of that. So arithmetic with polynumber on sequences, basically the same as arithmetic with polynumbers themselves. Alright, so let's have a look at Sloan's online encyclopedia of integer sequences. And let's look for some polynumber sequences that are in his list. Of course, he has many sequences in his list. But the sequence 0, which is, I suppose, an important sequence, it's actually number 4 in his list. So that would be incorporated in our framework. It's the constant on sequence 0. The constant on sequence 1 also gets a mention. It's sequence number 12 in his list. The on sequence that we're calling n, namely just the identity sequence 1, 2, 3, 4, 5, the sequence of natural numbers themselves, that's number 27. The squares is number 290. There it is there, n squared. The cubes, n cubed, is number 578. There it is there. And occasionally other polynumber sequences occur in his list. I was looking to see whether there was some place where one can sort of access all the polynomial sequences, if there's some sort of separate way of getting them. I couldn't find a way of doing that. Maybe there is. If somebody knows a way, that might be interesting. It might be interesting to identify which of the sequences on his list are actually polynomial or polynumber sequences. It's going to be obviously only a fraction of the vast number that he has. One of the ones that he does have is n squared minus 1. So the sequence of squares minus 1, which can also be thought of as sequence of products of, like this is 1 times 3, this is 2 times 4, 3 times 5, 4 times 6. So product of successive numbers separated by 2. This sequence here has, for example, other interpretations, and one somewhat amusing interpretation. It's the number of ways of interchanging hopping frogs and toads which are strung along a line with one space in between them. So for example, if you have 2 frogs on a line and 2 toads on this side, and you want to interchange the frogs and toads, and a move in this game amounts to either moving a frog or a toad, either left or right, or jumping over one of the others. So then it takes, in this case, 8 moves to go from this position to this position where the toads and the frogs have reversed. So the first move is you move this frog over one, and then the next stage this toad hops over that frog, and then at the next stage that toad moves left, and so on. And it turns out there are 8 steps that corresponds to that particular element in this sequence. So if you start off with 3 frogs and 3 toads, you might want to check that it takes 15 steps to interchange them. So bringing us again to this point that a sequence in, say, the online encyclopedia has many possible descriptions. There are many possible ways of thinking about what this sequence represents. With these polynumber on sequences, we are specifying a particular form for them. It really pins them down in a very precise way. So we know exactly what the sequence is. We have a canonical name or symbol for the sequence. Now most of the sequences in his list are not of this kind. So it's a natural question. Well, how do we deal with the other infinite sequences? How are we going to extend this kind of thinking to, say, sequences given by expressions that are arithmetical creations from n, but more complicated than polynumbers. For example, maybe n to the n, or maybe a recursive sequence. So this is actually quite challenging. And I give you something to think about, is how are you going to extend this kind of thinking to the next level? How do we go beyond polynumber sequences? And next time I'm going to point out some of the challenges in actually doing that. It turns out to be much trickier than one might like to think. Very serious hurdles in concretely, precisely extending this idea of ON sequences to more general sequences. So we'll talk about that next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.